Alright, welcome back. In the last video we talked about like what a vector is and all that. So now I basically have a bunch of gadgets set up that have various vector outputs, and we're gonna show those off and explain how they work and that kind of stuff to hopefully make it a little more clear like how vectors are used. We're gonna start with this controller sensor, specifically the sticks. So if I plug this left stick into the signal display, we can see it shows stick values. So if I go into play mode and I possess this block that has the controller sensor on it, and I start pressing the left stick in certain directions, you can see the numbers change to represent which way I'm holding the stick. So if I press the stick straight up, you can see X is basically 0 and Y is -1. If I press it down, X is 0, Y is 1. If I go left, X is -1 and Y is 0. If I go right, X is 1, Y is 0. So what this vector represents is how much left and right the sticks are and how much up and down they are. So here's another example. I took the color output on this box, the tint color, and I took the output and I hooked it into this node. So you see if we hook this up to the signal display, we get red, green, and blue. So color is a vector, and you can see if we change this to red, red is 1, green 0, blue 0. If we make it more green, no, we have red is basically 0, green is 1, blue 0. If we go to blue, then we get blue is 1, green 0, red 0. And every color you have in here can be represented in this vector. So if we go to yellow, then that's basically, you get yellow when you have red is 1 and green is 1. And you get like cyan when green is 1 and blue is 1, but red is 0. White is when all three are 1. Black is when all three are 0. Okay, so let's say we want the left stick to control the red and green value of the color. Well, we can just take the left stick, hook it up to a splitter, and then plug these values into the red and green and see what happens. And then for blue, we'll leave blue at 0 for now. So if we take that value and we hook it back up to the color input on the box, we can make the box actually change color. The next thing we're going to look at is this look at rotator, which if you're not familiar with that, this basically tells an object to turn and look at a specific tag. I don't have any tag I want this to look at, I just want to look at this specific scene space direction output. So if I hook that up, this scene space direction is basically the direction the object is either currently facing in or trying to face in. Since we don't have it looking at any tag, it's just the direction it's facing in right now. How do you define what the front of the object is? Well, you have this little arrow gizmo thing here, and you can turn and point this in whatever direction you want. Say like, if I want this face of the box to be the front, point the arrow this way. If I want this to be the front, point it that way. So if we set up the front of the object to be facing this way, which is to the right relative to the rest of the scene, we get a vector that has a value of X is 1, Y is 0, Z is 0. If I turn the object to face upwards like this, so that now the front of the object is pointing up, you can see if you tilt your head a bit that X is 0, Y is 1, and Z is 0. And again, if we point the object like off this way, we get something with a higher Z value. Or well, it's negative because it's pointing this way, but yeah. So that scene space direction gives you a value that represents the direction the object is facing in. Another similar output that shows the direction something is facing in is this laser scope. So a laser scope, if you weren't familiar, is basically just a line that points off in a direction if that line hits something, then it activates all its outputs. The output I wanted to look at was this hit surface orientation. So if we hook that up there, so we have this box. If we move it in the path of the laser scope, you'll see this little green arrow appear that's pointing off in this direction. This arrow is the hit surface orientation. It's just a vector that's pointing in the direction the surface is pointing in, basically. It points right off the surface. You can see a bunch of things. It's pointing mostly to the right, a little bit up, and not into the z-axis at all. So as I rotate this box, you'll see the hit surface orientation changes because the surface that the laser scope is hitting is pointing at a different angle now. But it's worth noting that this doesn't represent an angle. It represents a vector that is pointing in the direction defined by these x, y, z. When it comes to angles, you've got different stuff to deal with. So next we're going to look at a tag, because a tag has a scene space transform output. And something that's definitely worth noting here is that we were talking about fat wires in the previous video, and how they contain multiple other numbers. The thing is that some fat wires contain other fat wires. So scene space transform actually contains 3 other values inside of it. It has a translation, which in itself is a fat wire. It has a rotation, which is another fat wire, and it has a scale, which is not. That's just a single wire. So translation should make sense. That's just a vector representing the position from the origin, wherever that is. That's probably somewhere. The one I actually want to look at is this rotation output, because this one's a little bit confusing. So the rotation, if we experiment a little bit, let's turn on the grid and let's rotate this 90 degrees this way. You can see that we get 90 on the Y. Cool, that makes sense. We rotated it 90 degrees around the Y-axis. Remember, the Y-axis is pointing straight up. Like if we look at it from the positive x-axis and we rotate it clockwise, we get a negative value. If we rotate it counterclockwise, we get a positive value. So it looks like we just get the number of degrees we rotate around each axis, right? Okay, well, let's try rotating it this way and then this way. You'd think we'd get 90 on the x-axis and then 90 on the z-axis, right? Something like that. We get a whole bunch of 138s. Why do we get a whole bunch of 138s? Well, it's because this rotation vector, the direction that this vector is pointing in is the single axis that we're rotating the object around, and the magnitude, the bigger or smaller the numbers are, that represents how much we're rotating it by. So if we only rotate this a little bit, you can see things only change a little bit, right? And the direction that this vector is pointing in is what we're rotating this thing around. So the reason it was at like 130 or whatever, like 138 everywhere instead of just like 90 and 90, is because we're actually starting from this position, doing like one crazy rotation to get it like in this position. I'm not 100% how this works, but the way I think it works is that it sort of automatically chooses a vector that it's rotating around, which is what this is saying. Rotation is an axis angle vector. The direction indicates the axis of rotation, the magnitude indicates the degrees of rotation around that axis. Okay. We're not done with the freakiness yet. Something I realized is that if you zoom really closely in on this wire, we were talking about fat wires in the last video. If you zoom in here and count the colors, we have 8 different colors. 8 different colors, okay. When we split this up though, we got a vector with 3 values, another vector with 3 values, and a single value. That's only 7 values. Where is this mysterious 8th value? Well, another thing I learned by going into Ford's gadget is that you can force a splitter to have a certain number of outputs by hooking a combiner into the same input at the same time. So if I go here and say take a random combiner, set it to 8 to see what this mysterious like 8 wires is containing, and you can break it into 8 values, 8 individual values. I'm not going to do it myself. If you were to hook up all those values, which this gadget already does automatically, and I take this full scene space transform, here's everything we get. Ignore the last 3 because this gadget is doing like stuff. The first 8 values here is what is actually on this fat wire. The first 3 are the position, which we got from the splitter. The next one is the scale, which we also got from the splitter. And then we have 4 values for rotation in quaternions, rather than this like weird rotation axis angle vector thing. Quaternions are definitely out of the scope of this tutorial though. I'm not going to talk about those. You can look them up because they're useful, but they're another way of representing rotation that's kind of unintuitive. So I am not even going to try to explain it. Okay, so that's how rotation, that's the rotation you can get from the scene space transform on the tag. There's also an orientation output you can get from an angle sensor. So if we hook this up here, we get something similar where as we rotate this, the value increases as we rotate it more, and it sort of represents the axis that we're rotating something around. The difference here between the rotation we get from the tag and the rotation we get from the angle sensor is that this one only goes from 0 to 1, whereas this one, the tag, went from 0 to 180. So this gives you an angle. This one gets you a vector pointing in the axis of rotation, but the value, the length of the vector is from 0 to 1 rather than, you know, a number of degrees. Alright, so those were a bunch of like vectors in Dreams that you can use and hopefully not be confused by anymore. So now we're going to talk about how you can like manipulate vectors to get what you want out of certain things. See you then.